Hello everyone, and this is physics. In this video, I'd like to have a short conversation about electricity. Then I'm going to do a little talk about covalent bonds, ionic bonds, metallic bonds, and finish the video with a short demonstration. Speaking of electricity, our modern society is highly dependent on electricity. Take a moment and think about all of the items in your home that require electricity. Oh, no, take it back. Think about all of the items in your home that don't require electricity. That will be a much shorter list. Take, for instance, my office right here. I have electric lights, as you know. Over here is a light switch. And if I turn off the light switch, obviously I go in the dark. The thing about electricity, it is currently being generated. When I turn these lights on, the electricity that I am using is being generated in real time right now as I speak. When I turn it off, the power generation station is still operating. It's still making electricity. I'm just simply not using it. In order for me to use it, I turn on the light, and there it is. But it's being done in real time. Should that particular power generation or any line in between my house and the power generation itself, all the electricity in my home will be stopped. I will be in the dark. If we were all to lose electricity, we will go back to medieval times rather quickly. We are heavily dependent on electricity. So it makes sense to learn a little bit about electricity. Consider my home. I had some renovations done by an electrician some years ago, and I asked him to hang on to some of these wires, which I keep, and I have another one here. Now these wires are color-coded, and the color coding means something to the electricians. I can look it up, but there's also a yellow when I go to the hardware stores and see various codes, and they mean something regarding the wire that's in it. Okay. And in here is copper wire, as you all know, and the electricity flows through the copper wire coming to my home from the power generation. And there's also a sheathing on the outside of this one here being white. And when I touch the sheathing, should electricity be flowing through this, I am protected from that electricity. Should I touch the actual wire itself, well, that'll be a small problem. And the question is, why is that? Why is it that this copper wire is able to conduct electricity, and yet the sheathing that's here doesn't conduct electricity? Within reason, if I put enough voltage through this, it will go through the sheathing out here, but we don't operate in typical homes at that kind of voltage. So this is a conductor. The copper wire itself is a conductor, and this is an insulator. And the question is why? Why is one a conductor and the other an insulator? In order to understand that, we need to go down to the atom itself. And there are three types of bonds that atoms do. There's the covalent bond, the ionic, and metallic bonds. Let's have a look at the covalent bond. For covalent bonds, I'll just simply use, pick an element, oxygen. I'll use oxygen as an example. So this is covalent. And we know that covalent is the sharing of electrons. So I have oxygen. And oxygen, in its valence electrons, there are 6 valence electrons. Oxygen has a number 8, yep. 1, 2, 3, 4, 5, 6. This is oxygen, O2. We have positive nucleus and another oxygen. And it also has 6 electrons in its outer shell. 1, 2, 3, 4, 5, 3, 4, 5, 6. Covalent bond simply means the sharing of electrons in order to come up with 8 in the outer electrons. And having done this for oxygen, all of these electrons now are tied up, making that bond. They are not available for work. Let's have a look at ionic bonding. Ionic bonding. Now think of an ion, sodium chloride. Common one, sodium chloride, salt. Sodium has 1 electron in its valence. And then chlorine, being highly electronegative, has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Chlorine is highly electronegative, and it's going to pull this electron away from the sodium, thus making 2 ions. Sodium plus, because the electron is now going to go here to the chlorine. And then the chlorine itself, because it has an additional electron, becomes negative charge. And The negative and the positive will attract each other, and this is known as an ionic bond. Again, these electrons are being used in order to make this bond, and they are not available to do any work. Now let's go down and look at metallic bonds. Metallic bond. I can pick a metal, copper, iron, aluminum, all of them will follow the same path. So I'll just simply use, I'll go with iron for the time being. Iron nucleus, and iron, say it has 3 electrons, we'll go with iron 3+. Iron had 3 electrons in the outer shell. And another iron next to it, iron, and it too has 3 electrons, and another iron, and it too would have 3 electrons. And these electrons, right, they are free to move. This is known as a sea of electrons. Sea of electrons. And all these electrons, they are not restricted to one iron atom. They move about. That one can travel to this electron, that atom. This one can travel to this atom. That one can go there. This one here can come down here. They are free to move. Since they are free to move, if I put in electric potential, I'm going to add to it an electron, electricity, pushing it one way. Since these electrons are now free to move, they will bounce around and flow. And out at the other side, if I put in electrical charge on one side, that electrical charge will flow out the other side. Hence, a metallic bond will favor electric conductivity. What we have here in these wires, well, we have copper. Copper behaves the same way as I did here with the iron, the same thing. And it has a sea of electrons, and it will flow. So as a result, this was a good conductor. On the other hand, on the outside here, I have this one. This is vinyl. This is probably also vinyl. And vinyl is a covalent bond. And as you saw earlier, covalent bonds, those electrons are tied up in making the bond. Since a covalent bond, which is the outer sheathing of this, all these electrons are tied up making that bond, they are not available to do work. As a result, they are good insulators. They will not conduct electricity. Hence, we have this wiring, which goes through our homes, a safe sheathing on the outside, and electricity flowing on the inside here with the copper itself. I'll do a back. I'm going to think about here for a moment. Back around the turn of the century, 1880, 1890, 1900, when electricity was first being brought to the homes, power generation station, wires were being made, and the electricity was flowing through the power lines into the homes. At that particular time, this was the beginnings of electricity. They really didn't know all that much about electricity and how it flows and what it does in the wires. As a result, there were many electrical fires in homes after they got electricity installed in order to turn the lights on and off. The reason that they had all of these electrical fires, well, again, one is because, well, it was new. Everything was being learned. And the manufacturing of the wire itself, which we have here, this being 14 gauge wire, wasn't all that great either. It had thin spots. It'd be stretched, so it would have thin sections and thick sections. And the thinner the wire is, the less electricity it can support. And because the wire generation stations at the time weren't all that great either, they had spikes, and large electricity was being generated at one time, large spikes. Consequently, that combination resulted in electrical wire fires in homes. I'm going to do a demonstration of that right now. I just need to set up. And just like all new things, everybody learns from what's happening. It was a good thing having electricity, and it still is. Now I need my small little demonstration. This is hazardous. I do not recommend you do this in your homes. I'm going to pour some water into this beaker. And the demonstration I want to do here is that if you put too much electricity through a thin wire, the wire will burn. As a result, you'll get electrical fires. And if you're going to do any electrical work in your homes, I recommend you get a qualified electrician to do so. So I got some water here. I need some wires. There we go. I'm going to use steel. Steel is made up of iron. Hence the reason I chose iron for my little demonstration here. I have here steel wool. And it's very fine. Very fine steel wool. I'm going to take a piece of this. Rip it. Superman's got nothing on me. I can rip apart steel. Look at that. So I have here a batch of steel wool. And the reason I put water in here, that's for a safety measure. And I got some tongs in order to hold the steel. And I need the electrical source. And that is going to be in the form of a 9-volt battery. Simple 9 volts going to this. And let's see what happens when I put too much electricity into a thin wire. And hence we have electrical fires. Again, I say don't do this at home. And if you're going to do electrical work in your homes, get a qualified electrician. I'm just going to douse that here in the water. Having said all of that, and this is physics.